This is a brief review of Modern Physics Part 1, and in this place I'm just really looking at a quick review of problem solving and the intensity of photons and electrons being produced from the photoelectric effect. The problem we're looking at is a laser with a power output of 2 milliwatts at a wavelength of 400 nanometers, and it's projecting onto calcium metal. And how many electrons per second are ejected, and what power is carried away by the electrons given that the binding energy is 2.71 electron volts. Okay, I've got all my givens down and my two unknowns, and I've noted that the power is equal to work over time. Power is in watts, work in joules, and time in seconds. So 2 milliwatts is equal to the amount of work per second. And since we're hunting for the work done, or the energy given to the system, the work done is 2 millijoules for every second. Why are we looking for work done? Well, the work done is getting the electrons out of the metal, the photoelectric effect. And for every photon that hits the metal, we have 1 electron eliminated. So the work given to the system by the photons is going to correlate to the electrons coming out. But actually, the amount of photons we have is going to correlate to the number of electrons coming out. So we really just figure out how many photons you have in 2 millijoules. 1 for 1. For every 1 proton, you have 1 electron. How many photons are being generated by the laser with that 2 megawatt power? So over on the left-hand side, I'm starting to write the stuff down. E equals hf, V equals lambda f, my two guiding equations. But V in this case is the speed of light, or c. So c is equal to lambda f. Rearrange that equation for f, and f equals c over lambda. Taking that value of f, c over lambda, and substituting it into the equation E equals hf, I get E equals h times c over lambda, or E equals hc divided by lambda. So then I'm plugging in the numbers. I have to be careful what number I use for hc. I want to take joules per meter because I have my work in joules. And if I've got joules per meter, that means my wavelength has to be in meters too. So if you notice up above, I changed the 400 nanometers to 400 times 10 to the minus 9th meters. And I'm going to use that number and substitute that number into the equation, being careful that all my units work out. So I get the energy per photon is equal to 4.975 times 10 to the minus 19th joules per photon. So now I know how much energy I have for every photon, and I have 2 times 10 to the minus 3rd joules total every second. So that total amount of energy, each photon carries 4.975 times 10 to the minus 19th joules, so that tells me I have a total of 4.02 times 10 to the 15th photons, which is the answer to part A. Well, almost the answer. It asks how many electrons per second, remember? But there's that 1 for 1 ratio between photons and electrons, so the number of photons is equal to the number of electrons. Thereby, 4.02 times 10 to the 15th electrons is the answer for part A. And part B, I'm not going to do. We don't do it in our class. The retina of a human eye can detect light when radiant energy incident on it is at least 4 times 10 to the negative 17th joule. For light of 600 nanometer wavelength, how many photons does this correspond to? All right, I've got all my givens down. E equals 4 times 10 to the minus 17th joules. That's how much energy our eye will respond to, the minimum. The wavelength of the light coming in is 600 nanometers, and I want to know how many protons that is. How many protons did it take to make my eye see? Over on the right-hand side, I have that E equals hf, V equals lambda f, but V is just C, so C equals lambda f, and and rearranging it, lambda equals C over F. Therefore, substituting in, E equals HCF. I have to be careful about what value I use for my HC. My energy is in joules, so I want to have the energy per photon in joules also. So I've got 1.99 times 10 to the negative 25th joules per meter for HC. That means my wavelength had better be in meters too. So I put in 600 times 10 to the minus 9th meters for my wavelength. And that gives me the energy per photon is 3.317 times 10 to the minus 19th joules. Well, if that's how much energy I have for each individual photon, and it takes a total of 4 times 10 to the negative 17th joules for my eye to respond, now I'm just going to basically do a dimensional analysis thing. How many photons are there in 4 times 10 to the negative 17th joules if each photon has an energy of 3.317 times 10 to the minus 19th joules? So much easier if it was in electron volts. Anyhow, so I multiply them out. The joules are all going to cancel out, and it's going to tell me the number of photons I have. So I'm going to rewrite this over to the side. This is the number of photons I'm solving for, and that magic number is, it's only 120.6 photons. But you can't have a 0.6 photons, so that's out of there. It's only 120 photons. Maybe 121. It's going to be close. And that's the answer. And the end.